Welcome. In this video, we're going to be looking at maximum likelihood estimation for the scale parameter of the exponential distribution. So we're going to begin by saying we have a series of independent exponentially distributed random variables, x1, x2, all the way up to xn, and we're going to say they're IID, or identically distributed and independent. So exponential, and we're going to say that the scale parameter is lambda. The PDF, or the probability density function of all the xi's, or any of the xi's, is given by... So there are two ways that we can express the exponential distribution. One is in scale form and one is in rate form. In this case, I'm going to assume that our lambda here is the scale parameter. So we write that the PDF is equal to 1 on lambda e to the negative xi on lambda, and of course xi is only, or is strictly, a positive real number. Alternatively, if just as a side note, we could have also written this in the form e to the negative lambda xi. Now in this form, this would be in the rate, or we'd have lambda would be called the rate parameter, but we're in this blue part here. Now we're dealing with the scale parameter lambda. It's called the scale in this version. We're not going to deal with that green version. So in doing so, the likelihood function is given by, well, again, what is the likelihood function? Well, the likelihood function L of theta is given by the product I equals 1 to n of all the respective marginals, because we assume that they're independent. So in other words, or this product here is in fact the joint distribution of the xi, or of x1 to xn, but we call it the likelihood function. Another word for it is the likelihood function. And then we're going to replace I equals 1 to n. We're going to replace fxi given lambda here. We're going to replace that with our expression above. So that becomes 1 on lambda e to the negative xi on lambda. And now doing some more algebraic manipulation. So what do we have here? I'm going to split it up a bit. I'm going to say that's I equals 1 to n of 1 on lambda times I equals 1 to n of e to the negative xi on lambda. Now, why have I done it like this? Well, this ends up being, or this first term here, we end up multiplying 1 on lambda by itself n times. So this leaves us with lambda to the negative n. And here we've got the product of exponentials. So this would be something like times e to the negative x1 on lambda times e to the negative x2 on lambda times ... times e to the negative xn on lambda. And what we're going to do here now is to do a bit of simplification. We know our power laws. We know that when we've got the base here, which in this case is e to the power of something times the same base to the power of something times ... Our power law says that we can just add all the indices together. And so what we end up with is equal to lambda to the negative n exp of the sum of all of these terms. So what I'm going to write that is negative x1 on lambda minus x2 on lambda minus dot 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 minus xn on lambda. And finally, after some simplification, what I'm going to turn this into is negative lambda exp. Now I can take you'll notice here there is a negative 1 on lambda common to all of these expressions here. So I've got a negative 1 on lambda, so I can take that out as a common factor, 1 on lambda, and what I'm left with is the sum of x1, x2 up to xn. So I'm going to rewrite that as I equals 1 to n xi. And now we have derived the likelihood function. So now our goal will be to find the log likelihood function. So the log likelihood function is given by, so by definition, what is the log likelihood function? Again, I'm going to use the symbol lowercase l of lambda. Well, the log likelihood function is log l of lambda. Remember here that the log in this case refers to log base e by default. So now what I'm going to do here is I'm going to take my expression that I found for the likelihood function, which was this expression there. I'm going to plug it in here, negative n exp of negative 1 on lambda, sum of I equals 1 to n xi. Alright, we're getting somewhere here. Now we're going to use our log law. So remember that log of a product is equal to the sum of logs. So in other words, we can now rewrite this as log, or we can say that these two terms are multiplied by each other inside the log. So we've got lambda to the negative n and exponential here. So we can say that's the sum of log lambda to the negative n plus log of this exponential term inside. So I equals 1 to n xi here. And so now we're going to use a bit more of our knowledge of the log laws, or our logarithmic laws. When we have a power, remember we can bring that power down the front of our logarithm, so that becomes equals negative n log lambda. Now, here we're taking log exponential. So because we're doing log exponential, remember the log is the inverse of the exponential. So when we take log exponential, we actually just get left with whatever's inside the exponent power, which is, in this case, negative 1 on lambda, the sum of I equals 1 to n xi. And now we have also found an expression for the log likelihood function. In this case now what we're going to have to do is we're going to have to differentiate the log likelihood function, solve it equaling 0, and then prove that that is a maximum. And we will do that using the second derivative. So now, for now, what I'm going to do is I'm going to find the first and second derivative of this expression here. So, differentiating with respect to lambda gives, okay, so first we're going to find the first derivative, dl of lambda over d lambda, which in this case, okay, so we're looking at our first expression here, negative n log lambda. How do we differentiate that? Well, n is just a constant in terms of lambda, so all we have to do is differentiate the log of lambda. Now, the differential of a log is 1 over, so 1 over lambda, so it becomes negative n on lambda. And of course, the sum of xi's is also a constant with respect to lambda, so all we have to do is focus on differentiating 1 on lambda. Now, 1 on lambda, the differential of 1 on lambda is actually negative 1 on lambda squared, so then that becomes, the negatives cancel out, and we end up with plus 1 on lambda squared, and of course we still have the terms I equals 1 to n xi. And now, again, what we're going to do is we're going to find the second derivative with respect to lambda. Now, this will come in handy afterwards when we have to prove that it's a maximum. And so here we're going to do the same thing here. What is the derivative of negative 1 on lambda? That actually becomes n on lambda squared. And now we have to differentiate 1 on lambda squared. Remember, that's the same. Of course, that's the same as lambda to the negative 2. So what do? We take the power down the front, negative 2 down the front, 1 off the power. So we end up with negative, well, change that back to blue. We end up with negative 2 on lambda cubed, the sum of I equals 1 to n xi. Alright, so we found the the first and second derivative. So to actually find the maximum likelihood estimate, so to find the MLE of lambda, which we will label lambda hat, we have to solve the following equation. We solve dl, or the first derivative with respect to lambda evaluated at the MLE is equal to 0. So now what we have to do is we have to take this expression for the MLE up here and substitute in lambda hat and then solve that equaling 0. So if and only if negative n on lambda hat plus 1 on lambda hat squared, sum of I equals 1 to n xi equaling 0. Now we're going to do a bit of rearranging here. The first thing we're going to do is we're going to take this expression to the other side. So that'll give us 1 on lambda hat squared, sum I equals 1 to n xi is equal to n on lambda hat. That's actually it. So again, continuing with our solving here, what are we going to do? We're actually going to multiply both sides by lambda squared, or lambda hat squared on n. And by multiplying both sides by lambda hat squared on n, we actually are left up with lambda hat equals 1 on n sum I equals 1 to n xi, which by definition is again the sample, or is the sample mean. So we've solved it equaling 0, and we've found an expression for lambda hat, which is the sample mean. So now our goal will be to show that this is a maximum. So to show that it is in fact a maximum, or I should say, to prove that L of lambda is maximized, for lambda equals lambda hat, which in this case is xn, what we have to show, we must show that the second derivative, so d squared L of lambda over d lambda squared evaluated at the maximum likelihood estimate is less than 0. Now, let's actually work that out. So, the second derivative, L of, or lambda, the second derivative evaluated at our estimate is equal to, okay, well, let's find our expression here. So where's our, here is our expression all the way up here. Copy that expression and we're going to take that down here. So we're evaluating at lambda hat, so instead of writing lambdas here, we're going to write lambda hats. Now, lambda hat, what did we say lambda hat was? Well, we said nicely that that was equal to the sample mean, so I'm going to replace that with sample mean squared minus 2 over sample mean cubed times. Now, the sum of xi's, and very on the side here, what we can write is that, remember that 1 over n of I equals 1 to n by definition was equal to the sample mean. So, in other words, if I take this n on this side and I multiply it across to that side, what I get left with is still the sum of xi's is equal to n x and x bar. So instead of writing the sum of xi's here, instead I'm going to write this as n x bar. And why do I do that? Because now I see that this nicely cancels out with this expression here. So what we're going to be left with is n on x n bar squared minus 2n, so we're still multiplying 2 times n here, but we've got this xn bar and cancelling with one of the xn bars down the bottom here, which leaves us with xn bar squared. And now you'll notice that the denominator is the same here, so we can actually, or this has a nice closed form. This just becomes negative n on xn bar squared, which, surprise, surprise, is less than 0. Why is that less than 0? Well, xn bar is definitely, well, x, if you remember x all the way from all the top here, all the x's are positive, so therefore their sum is also positive, or they're squared. In fact, I could easily say that the square of any number has to be positive, so it's got a positive denominator. N is a number, it's a natural number, it's the number of observations, always has to be positive. So we've got positive over positive, negative at the front, therefore it has to be less than 0. And so we've proven, essentially, and so the MLE of theta is given by our estimate here, and I'm going to put a capital X bar here instead of a lowercase n that we've solved up the top, and this is the proof of the MLE of the exponential distribution, the scale parameter.